Okay, well today we get to do a lot of stuff with matrices and vectors. Yes, this is exciting. Okay, so let's just talk a little bit about vectors. Okay, and so we could have some vector x sub n. And we can represent it, with a vector by putting this little, this little arrow above it to say it's a vector. In your textbook, it's a bold lowercase letter, but when you write in paper, it's hard to say something is bold print. Okay, and this would be something like x sub n1, x sub n2, and x sub n3, okay? And in this case, x sub n is, an element in three-dimensional real space, right? So vector x sub n is an element and we can also write it this way. And use the transpose operator there, okay? And meanwhile, we also have matrices. And matrices, somehow we have to denote that this is capital, bold. So I put all the little serifs on it. It causes, writing things to take a bit longer. But, well, how do you guys denote a capital bold print letter in your thing, in handwriting? It's often difficult. So I use the serifs. I know there are different methods, and some people don't even bother with this. But, this would be A11, you put the row first, then the column. So this is A12, A22, and A32. You put the row first and then the column, and that would be a matrix there, okay? I'm hoping my handwriting is legible. You guys can see the screen good? Okay. Screen well, okay. And so let's put this back in the context of linear regression or linear modeling. Okay, and so we said our outputs, we have a function of x of n with given parameters w0 and w1, and we said our linear model will produce w0 plus w1 times x of n, right? This is our intercept plus slope giving our linear regression, okay? And here we can and in this case, we have the function this way. We can write this in vector notation. Okay, and instead we're going to let the vector w be w0 and w1, and we'll let the vector x of n be the vector 1 and xn, okay? And thus W0, W1 being this thing can now be a function of vector xn given our w vector, which is going to just be our w vector transpose xn transpose. Okay, does that work with everybody? If I do w transpose will be w0 comma w1 times, here actually let me, and so wt transpose x n will be and then so observing the rules of matrix multiplication we get. Okay, so we can put our linear regression model in the form of in matrix notation here. Okay, and again we want to find the set of parameters that will minimize our loss function. Okay, so did I flip the page too quickly? Okay, I apologize. Just let me know when you guys are ready, and we'll go. Okay, we ready? Yeah? Okay. Well, we're doing all of this matrix stuff so that our lives will be easier in the future, okay? Just trust me on this, okay? You know, it's like, oh, you know, I like to count up to 10, you know, I don't want to have to learn how to multiply and stuff like that. But it's like, no, learn the multiplication, it'll make your life easier, okay? Rather than just sticking to addition. It's a little bit like that, but but different. Okay, so, you know, we wish to find the model parameters W0 and W1, or really just find the model parameter of W hat that minimize the loss function. Okay, so what was our loss function? Okay, so the loss function will be the, you know, average squared residual. And so that's going to be 1 over n. So we'll say our loss function is 1 over n, where we add up from 1 to n, all observed over all observations, t sub n minus, and we can, well, I guess I'll first write in what we originally had, w0 plus w1 xn squared, but now I'm going to just replace this part becomes w transpose xn, right? And that's what we have, okay? And by using vectors, I can get rid of this sum from n equals 1 through n of t sub n, okay? So I can say, I'm going to say t vector is going to be, you know, t1, t2, Tn, right? So this is going to be the vector of T1 through all of this. All of our, this is actually T capital N, okay? There, let me, trying to be proper with my notation there. Okay, and so I can put that in there, and then I will now have T vector minus W transpose okay, wait, actually, before I get there, by using vector and matrix notation, I'm going to have the matrix X. The matrix X will be all of our X observations. So this will be, this is a matrix of vector x1 transpose, vector x2 transpose, dot, 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 x cap n transpose. Okay. Here. Let me just put this into vector notation, vector and matrix notation, and then I'll explain all of this stuff here. Okay. So we can replace this with just 1 over n, and we're going to have vector t hat minus you have capital X W transpose times minus okay, so this is what we have. So using, this is still our loss function, so this is now in vector matrix form. We can get rid of the summation. Okay, because vector multiplication does the summation for us, right? So let me just show you how this works. So we have our, you guys just need a second to catch up here? Are we okay? Okay, so we've got our vector t. These are all of our observations. So this is t1, t2, all the way up through tn. Okay, and then our matrix X is this. It's our vector x1 transpose, vector x2 transpose, so on up to vector xn transpose, which becomes, in our case, our x vectors are 1 and x1, right? So this is 1 and x1, 1 and x2, up through 1 through xn. Okay. And the omega, or not omega, W matrix is W0 and W1. Okay. So when we talk about doing X times W, we have this thing times this thing. Is this equal to 1, 1, dot, 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 1, x1, x2, dot, 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 xn, times W0, W1. All right, and so this will give us w0 plus w1 x1, w0 plus w1 x2, so on and so forth up to w0 plus w1 xn. Okay, so this is what we have here. And so if we look at this, this is a n by 1 column vector. And this is also an n by 1 column vector. Okay, and so here I've got an n by 1 column vector minus an n by 1 column vector. So this part is an n by 1 column vector. This is an n by 1 column vector. If I transpose this and I multiply it by this, what do I end up getting? Well, I'm gonna, can I flip to the next page, or are you guys still writing? Yeah, I didn't hear anything. I can flip, okay. So so we've got, right, so we have this minus xw transpose times minus xw, this, okay? And so this thing becomes, this is a n by 1 column vector transpose, right? Okay, and so this thing is going to be t1 minus w0 plus w1 x1 minus w0 plus w2, I'm sorry, w1 x2 dot 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 up to tn minus w0 plus w1 xn. Okay, and so this is what it is, and then we transpose this, and so basically you're going to have, it's going to be 1 by n times n by 1, and when you do this, what are you going to get? A 1 by 1, right? A 1 by 1 scalar. This is a scalar. Okay, and then so thus our loss function is reduced to a scalar. Okay, so the loss function is indeed 1 over n times this is a scalar. All right, and so, you know, if we wanted to expand this, we can do this, and so this will become applying the transpose in here. We have t transpose minus so we have that times that, and then so now we just have a bunch of I don't know, multiplication to do. Okay, so we do the first, and we get t transpose t outer, so we get minus t transpose xw, and then the inner so this thing, whoops, times t over here, and then the last. So we have Okay. Is this all right? We're just doing matrix algebra, right? Fun times. Okay, and then all right, and then so now I can combine some of this stuff here. Let me just show you that. So I'm going to look at this thing right here. So I've got x this transpose times this. So this becomes when you apply the transpose, you have to switch the order. So you get the w hat transpose and then x itself transpose times that. We have that there, okay? And then when I look at over here, if I transpose this, I've got t hat transpose x and w hat. And if I were to just transpose this, this is going to be, this will also give me w hat transpose x transpose and then t. No, w transpose x transpose t. So these two, and if we look at these are both scalars, so we can combine them. Okay? So this is a scalar. Okay, and so when you transpose a scalar, it doesn't affect it. Okay? So you can transpose a scalar. This is a scalar, this is a scalar, this is also a scalar, okay? They're both scalars, so, you know, so we can transpose without changing the value. Okay? So all to say, this thing and this thing can be combined, okay? So that means this and this can be combined. All right, and so in our resulting thing, let me just slide this down a tiny bit. So our resulting thing ends up being t transpose t minus 2. And I'm going to use this, w transpose x transpose t plus, and I'll distribute the transpose here, so I get w transpose x transpose x w, and there you go. Okay. And we can also, you know, we can look at all of this. This is 1 by n times n by 1, right? And all of this all reduces to a scalar as well, okay? If you do the dimensions. This is 1 by n times n by 1. So that's a scalar. And this is going to be 2 times w transpose is 1 by 2. And this is going to be 2 by n. And over here we have times n by 1. Okay, so all of these dimensions line up so that this reduces to a scalar, and then this one also. This is 1 by 2, 2 by n. This is going to be n by 2, and w is 2 by 1. Okay, so everything reduces to a scalar if you match up the dimensions. So scalar value. Which makes sense because this is a loss function. We're just trying to calculate some kind of scalar value based on all of this. Okay, so basically now we have our loss function in matrix form here. Is this okay? So, I mean, this was our loss function up here, and we just expanded it out, and we have our loss function here. Okay, and it's still in matrix form there. Yeah, question?
How do we combine the two scalars in the middle?
How did we combine this one and this one?
Yeah, was it
Yeah, that's what this is. This is what I'm trying to explain here. You know, so over here I've got XW transpose XW grouped transpose T. That's this. That becomes that. And this, when I transpose this, it becomes this. And because this is a scalar, I can transpose it without worrying affecting the value. Okay, that's what I guess this is how we combine the two middle elements. Two values. Okay, is this good? Okay, so all of this just to get our loss function in matrix notation, okay? And the reason why we wanted, you know, here I'm still using W being W0 and W1, but you can imagine if, you know, I have a multiple regression model where I have like 7 or 10 W elements, okay? When it's in matrix form, all of it is all the same here, okay? It's gonna still look like this whether W has 10 elements or just 2 elements, okay? Whereas in the other form, it gets much, much, much bigger, right? So in matrix form, whether you have 10 elements in W, as long as, you know, if you have 10 elements in W, then your X matrix will now have 10 columns, yeah, 10 columns, and so everything, you know, gets affected that way. But as long as all those dimensions line up, it stays in this form here. Okay, so let's talk about taking derivatives of our functions with respect to vectors, okay? Because, so just to put everything in context, last class we didn't do this, but did your TA go over this in section? Doing the derivatives and showing how we minimize the loss function that way, right? So, you know, you're taking the derivative, you set that equal to 0 to find the thing. So we're going to do the same thing, okay, but this time in matrix form, okay? So we're going to, you know, taking derivatives. Okay, of functions with respect to a vector. Okay, have you guys already taken classes where you've done this already, or not really? No response. Okay. Yes. Okay. So some of you have, and so, you know, if this is review, just bear with me here. Okay. So we can take the derivatives of a function with respect to a vector. Okay. So we have the loss function. Okay, the loss function is a function of ... we have our data vector t, or I guess our data output vector. Our model, which itself is a function of the input matrix X and parameter vector W. Okay, so this is what we have here. That's our loss function. Okay, and we will treat with kind of our least squares regression. We will treat the output t and input x as fixed values. Okay, and so we are interested in seeing how our loss function behaves with respect to our model parameters w. Okay, and so just if you think, recall from calculus, when you have a function of one variable, when you have a function of one variable, the derivative tells you how the function changes with respect to that variable. Okay. And likewise, when you have a function of a vector, which is what we have here, we can set our t and our x as fixed values, and it just becomes a function of the vector w. Okay, so with of a vector, okay, the derivative of the function which we'll call the gradient, tells us how the function changes with respect to each component in the vector. Okay, and so here we will say the gradient. The gradient is the derivative of a function. We'll say a function that outputs a scalar, like our loss function. With respect to a vector. Okay. So we can say we have some function of a vector, right? So we'll say we have f of some vector w that exists in n space, right? So w, for this sake, we'll just start with w1 rather than w0. So w is an element in n-dimensional real space, and so we have some function w, and what this function w is, it maps values from n-dimensional real space to scalar values, right? So the function maps values in n space to scalar values in real space. Okay. So far, so good? Okay, so this is what we have, and we want to take the gradient of this function, or basically just we're going to take the derivative of this function with respect to a vector. Okay, can I flip the slide? Not yet. Okay. All right. I'll let you guys catch up. And like always, I'll post these notes online. Okay. Oh man, we're gonna run out of time here. Okay. Can I keep going? Okay. So the gradient of f of w with respect to w, we will say is the gradient of f is the derivative of f with respect to w, okay? And this itself, so f outputs a scalar, but the gradient is a vector. Okay, so gradient of f is a vector in n space. Okay, and in each of these things, the partial, so each component is the partial derivative each component is the partial derivative, so thus df with respect to some element wi, we'll say is the limit as delta goes to 0 of f of w1 up through wi plus delta wn minus f of this, I guess, times 1 over delta. Okay. So that's what we have there, okay, as our partial derivative. All right, so let's do a simple example here. Okay, so let's say we have some function of w, which we'll say is w1 squared plus w1 times w2 squared, okay, where here our w is a two-dimensional vector here, okay? And so we'll say, what is the gradient of f at 1, 1, okay? And so in this case, we have the gradient of f is going to be with respect to W1, the partial with respect to W2. All right, so looking at this, what is this with when I take the derivative with respect to W1? This becomes 2W1 plus W2 squared, yeah? Okay, and then when I take it with respect to W2, this goes away, and this becomes 2W1 W2, okay? So if I evaluate f at the point 1, 1, then this becomes, you know, I'm sorry. Okay, if I take f at point 1, 1, this is the partials at 1, 1. Okay, and now I plug this in and I get the values 3 and 2, 3, 2. Okay, and this again is a vector in two-dimensional space. So when you take the gradient or the derivative of a scalar function, a function that outputs a scalar, with respect to an n-dimensional vector, the result will be an n-dimensional vector. Okay, we're running out of time here, so we'll continue on with our discussion of taking the derivative of the loss function. Now that we have the loss function and we understand how to take gradients here, we'll apply that concept to the loss function here. Okay, we'll see you guys on Friday.